Hello there, this is a run through of the Equilibrium of Forces practice questions. Question 1. There are three forces on the jib of a tower crane. These are the tension in the cable, T, the weight, W, and a third force F which acts at the point X. See figure 1. So the crane is in equilibrium. Sketch the triangle of forces. And so the triangle of forces will look like this one here, should look like this one here. And why is it like that? So we know the forces that we're given. We're given the weight, which acts directly downwards. We're given the tension, which acts in that kind of direction. And what we can do with vectors is we can move them around, we can slide them around, so long as we maintain the length of the arrow and the direction of the arrow. And what we've done there is we've aligned the two vectors tip to tail, and what we then know is if the system is in equilibrium, the third force will close this triangle, so that it's a closed triangle and brings the system into equilibrium. And so that's the triangle that we're asked to draw there. And just to point out that this force would be acting at point X and would be, as shown in our diagram, in that sort of direction there, but that's not needed for the mark here. Question 2. Two forces of 5 kilonewtons are towing a boat, as shown in figure 2. The boat is travelling at constant speed. Sketch a triangle of forces showing the towing forces and the drag force acting on the boat. This is 1 mark. First thing to identify is the boat is moving at constant speed, and constant speed is an example of equilibrium, so the forces will be in equilibrium. The second thing to do is to start our vector triangle with the given forces. So we're given one of the pulling forces is shown here at an angle of 15 degrees, and that's we're told 5 kilonewtons, and we're then going to, so that's that one there, we're then going to move this one into a position where it's aligning tip to tail with the first vector, and that's also 5 kilonewtons. So with vectors, so long as you keep the direction of the arrow and the length of the arrow the same, you can slide them around, and we can align them tip to tail like this, and then to close the triangle we will find the drag force. So this arrow here is now the arrow which is representing the drag force vector. So the drag will be in the opposite direction to the motion, which we would expect, and it will be equal and opposite to the sum of the two 5 kilonewton vectors. So there's your answer for 1 mark. Question 3. The figure below shows a wooden block motionless on an inclined ramp. The angle between the ramp and the horizontal is theta. Part 1. The weight W of the block is already shown in the figure. Complete the diagram by showing the normal contact, reaction force N, and the frictional force F acting on the block. And so we know the normal reaction force N is always perpendicular to the surface. So in this case it's going out perpendicular to the ramp. The friction force must be up the slope because the block is motionless, stationary, and if it's stationary then it must be in equilibrium in terms of the forces acting up and down the slope, and we know that there will be a component of the weight acting down the slope, and the friction must be up the slope in order to balance that. Part 2. Write an equation to show how F is related to W and theta. And the answer is F equals W sine theta. And the reason for that is that we're looking at the opposite side of this right angle triangle, where this is the angle theta. And so using our trigonometry, we can say sine theta is equal to opposite, and we'll write this as F because we know it's equal to the friction up the slope over hypotenuse, which is the weight, and so F equals W sine theta. So question 4, we're given a situation and we're asked to draw a free body force diagram of the forces acting on the child for 3 marks. And so there are 3 forces involved. We've got the weight acting directly downwards, always. We've got the force, which is we can draw to the right, and that's the parent holding the swing. And then we've got the tension in the swing, which is labelled there at an angle of 40 degrees to the vertical. Part B, determine the tension in the swing. Right, so we're given the mass, which means we can find the weight from mg. And so the way to do this one is to find the vertical component of the tension, which is T cos 40, and then make that equal to mg, the weight. So we're looking to find this component here, and we're given the hypotenuse. So we want the adjacent, we're given the hypotenuse, we're going to be using cos. So cos of 40 is equal to the vertical component of the tension over the hypotenuse. So the vertical component of the tension is equal to T cos 40 degrees. And we're then making that equal to mg. We're then putting in the values that we've got. We can rearrange it first. So T equals mg over cos 40. Put the values in for the weight there, 25 times 9.81 over cos 40 equals 320 newtons. So that will be 2 marks. And part C, find the force F with which the parent is holding the swing. And so we need to find the horizontal component of tension there, and that's going to be T sine 40 degrees, and we're going to make that equal to F. And then once you've got that, we know the value of the tension, and we can substitute that in. Just calculate the value, and we should get 205 or 206 newtons. And so the reason that this is T sine 40 is the horizontal component is because that's the opposite side in the triangle. So if we just look at that, let's just draw the triangle here. We've got the hypotenuse, which is the tension. We have got a vertical component, which we calculated down here, and we've got the horizontal component that we are trying to find, and that's our angle theta. So sine theta is equal to the one we want to find, which we can call T horizontal over the hypotenuse. And so T horizontal is equal to T sine theta. And so we put that in there as T sine 40 equals F. And well done for completing this set of questions.